Hear ye, hear ye. A new proclamation from the ruling council of Her Majesty's government. You shall not go to school. Wait, no, you shall go to school. Oh, we got a new message. You shall not go to school. Instead, you will learn via the interweb. Bum. Who's that? Oh no! Lady Liberty, what are you doing here?
I'm here to defend life, liberty, and the pursuit of happiness. Prepare to be liquefied.
Ah, it's only a flesh wound. Come on, I'll still give it to you. I'll fight you back.
That's what you think. Now for step 2. Prepare to be vaporized.
Liberty wins out again.
I'll condense and be back. And then I'll freeze and be able to take you on once more, Liberty.
Hey there, grade 5. This is the next video that we're doing here. So this is just, again, a review. Basically, Monday is like review day, getting us back into the work mode here. And you'll have a little experiment today as well. Hopefully that goes well. So today we're reviewing what we've learned so far in changes in matter. So yeah, we kind of had a big long break again. So we're just going to go over it. So there are 3 states of matter: solids, liquids, and gases. They all live in, well, on Earth you can find all 3 types of things, and water obviously is found naturally in all 3 forms all over the place. So right now, I don't know, I'm pretty sure you'll have some snow outside, maybe not that much left anymore, but hopefully a little bit. And then, you obviously have seen lakes before, and it might have rained on you a few times, and you've seen some clouds. So we've seen all these things before. Here is a nice picture of a solid ice cube. Nice to go with your Coca-Cola. Some liquid, obviously, nice water. Sometimes you have ice in your water. And then you have a gas, right? That's like clouds and whatnot. So solids. Solids are commonly hard objects. However, they are not always hard, like a sponge. If I smack you with a sponge, it's probably not all that hard, but it is solid, right? Solids may retain their shape unless acted upon by external forces. So a sponge will kind of plop back to its actual shape eventually, even if it has the imprint of your face in it for a little bit. But I digress, right? So no, solids are generally harder. They kind of hold their shape together unless you smack it with something, right? A chair generally stays very chair-like until you hit it with an axe or something, because you want to make some firewood or some kindling. So this is very important to know that, solids are generally solid, and that's why we can say sometimes we use this as an adjective, like you're a solid friend. That just means someone who's sturdy and who's there for you, right? So with solids, the molecules or atoms are packed tightly together, right? There's not much space. I sort of think of it, I don't know if any of you know, but in the Greek world, they had these things called phalanxes. Phalanxes were these big, fortified structures, or a unit of soldiers that were really tightly compressed together, and they all had a bunch of spears in front, and that was kind of a phalanx, and they were really stuck together, and they were able to push off the other enemies. So these guys are all really nicely compacted together, and they're a solid force. They're not lacking any cohesion. Now, on the other hand, you have liquids. So we know many different kinds of liquids: water, juice, blood, liquids, they normally take the shape of their container. So if you pour liquid into a glass, right, it's normally going to take up the shape of that container. It doesn't really keep its own shape. Water, you wouldn't say, has like much of a shape by itself. Right? It fills up things. But these liquids are still kind of one unit, right? There's still some bonds together. That's why if you can siphon water, because it pulls on the other water, and they generally try and stick together, and it doesn't just go everywhere. Now, what's happening here is that when it's heated up a little bit, they lose their connection. But we'll get into that shortly. So yeah, liquids move around a little bit more. They're not as solid. So if you compare this one, the previous one, nice tightly packed, to this one up here now, they're not as tightly packed. So again, considering some sort of historical unit, you might think of the barbarians that the Greeks would fight sometimes. They would come at them much less together and kind of washed around them, and the Greeks would be able to push them aside often enough. So yeah, if you don't have cohesion in your military unit, it can make you a bit more susceptible to being pushed around. Just why, like liquid, it can get pushed through. You can move your hand through some water, right? Unlike, you can't just move your hand through a block of ice, unless you're got a very strong hand, I guess, and you smash the ice, but that doesn't count. But okay, so yes, that's the deal with liquids. Okay, gases. P.U. Who did that? No, not those kind of gases. Well, I guess those kind of gases count. So gases are different than liquids in that their atoms and molecules are even farther apart. So look at these guys. These guys up here in the yellow thing, they're not even bound together. There's so much energy that they're just doing their own thing. They're spread out. So what gases do, they're far less dense, but less dense than liquids. So normally if you put them in a container, they'll fill up the entire container. They just go everywhere around in the container. This is very different to liquids that fill up a certain set part of it, but they're normally, it'll sit at the bottom, right? The gas will go everywhere inside the container. Now, even in our book, it actually says that gravity does not affect gases, which is not really true. I don't know if it was trying to simplify, but right, we have gas giants, which are big giant planets of mostly gas, and obviously the gas is being drawn in to the planet, right? So you see here Jupiter. Gases are still impacted by gravity. That's why our atmosphere doesn't just go running away. They're just not as affected because they're less dense, right? Each molecule is on its own, doing its own thing, and so they're less dense. They're kind of bouncing around. So they don't have as much. They're not as pulled down to the ground, so they will go up a lot more and a lot easier as they weigh less. So that is the big thing with gases. They are very highly energetic and they are bouncing all over the place, and because of all that energy, their bonds are non-existent. So how do changes of state occur? Well, so all matter can change from one state to another. In order to change those states, something has to happen to them. Either heat, pressure, or cold has to be applied. So, for example, if you wanted to turn water into an ice cube, you would just put the water into the little ice cube tray and then throw it in the freezer, and the freezer would cool it down until it turns to ice, right? So that is how you create an ice cube, and that is called freezing. And then obviously vice versa, you can throw the ice cube out onto the outside in your room, and eventually the ice cube will melt. Or if you put an ice cube in your mouth, it'll melt even faster. So melting is something we all know, right? Melting ice cream cones is something we can remember from the summer. So we encounter this on a regular basis. When we have an ice cream on a hot summer, we notice this really quickly, right? And that's why we try and lick it around, eat it up as fast as possible, so we don't lose half of it on our hands. And so we actually notice in real time how the heat is changing the state of our ice cream, tragically. So yeah, we see that as the sun's energy is hitting our ice cream, it's warming it up, and as it warms up, the particles inside of the ice cream start to jostle around a bit more and a bit more. I remember we did that little game in the class where you're all supposed to hold arms, and then at first you're just gently jostling, and then eventually you're wildly jostling, right? So the bonds start to weaken a bit as you start to jostle. It's a bit harder to stay close together, and that's why it kind of loses its form, right? It starts dripping down. Now, if you had a container that you plop this ice cream into, or if you've ever had ice cream in a bowl and let it melt a bit, you'll see a liquid at the bottom at the end once it's done melting. And this liquid is just acts like a liquid, right? You can move it around. It kind of sticks generally together, but it is liquidy, right? And it takes the shape of the container, right? So if you put that ice cream ball in the container at first, or in your bowl at first, it still looks like an ice cream bowl and it's holding that shape. As it warms up, it starts to lose its shape and it takes the form of whatever it is in, container it is in. And that's why you see up here in this picture, right, when you throw ice cubes in there, they keep their shape. As it gets warmer, they will just lose their general structure and then turn into water that fills it up. So the bonds loosen. Now, when you do the other way, freezing, this is something we also encounter all the time, especially at this time of year, even though this year does seem to be a bit warmer. If you live by a lake or a body of water, which I grew up by a lake, and so we always see from our deck that the water is freezing around the edges normally, and as it freezes over, you can watch that happen day by day. This slowly happens as the water cools. What's happening is the water is starting to lose energy, and so the atoms are starting to draw in closer, and those bonds are now stronger because they can actually hold these things together and hold them still, and then they form like a solid object, right? They form a solid sheet at first, a sheet on the top, and eventually you can drive trucks over this ice, right? It gets so solid and so thick, right? So that is really, really cool. As they lose energy through the process of freezing, it freezes into a solid. The next one we're dealing with is evaporation. This is something that we should kind of know because of all of our, this is really big in our in our weather unit, which we just finished up. So we should have a general idea of evaporation. So when the sun is shining and it's a nice warm day, you might notice that if you come out in the morning or certain times of the day, you can actually notice steam coming off of the water. If you see a puddle or you spill some water out on some black pavement during a hot sunny day, you'll notice that the water will quite quickly disappear, and that is because it's evaporating. So what's happening is as the water is being heated up, the particular molecules are getting more and more energy in them, and they start to jostle around even more like crazy. They're wild, and so they actually break all bonds of they just kind of go off and do their own thing, and they start to float up because they get less dense. So each individual molecule is getting kind of separated from the others, and then it is able to start floating away. And so they don't hold together anymore, and these become a gas. So again, it's all about this heat and energy. Now, on the other end, when that energy is taken away as it goes up in the sky, right? We learned that as you gain altitude, it gets cooler, right? That's why mountains have cold, they have snow on the top often. So as you go up into this cloud way above the earth, you start the vapor starts to cool down, and as it cools down, it starts to condense back into a liquid, right? So it condenses, it gets tighter, and the energy of the individual water molecules begins to drop, and they begin to be able to form bonds again. Not tight bonds of a solid, though that does happen in the form when you get hail, right, or snow. So they form these little into little water droplets, and eventually they get heavy enough to fall to the earth, which is quite yeah, quite amazing. That's rain, and we have this nice picture here of some rain, and that's really important to our water cycle. And again, we can remember, these cycles, they don't just happen on their own, right? The Lord moves everything, and there's what's really interesting is there little grains of sand that the water droplets form around, so it is pretty incredible how it all, or it's not sand necessarily, dust or particles in the air, and it forms along those. And so really you see the just how amazing creation is. Even in the clouds, even in the rain droplets, right? We can have a little bit of awe, or a lot of awe rather, for our Lord and all that He has done, right? And He still governs this every day. So we need to remember that right, the Lord is not some distant figure who just made the earth at one stage and then stopped caring about it. No, the Lord is caring about it every moment. And sometimes we think we kind of put our own sort of ideas about who we are as a person onto God, but we have to remember God is infinitely grand, so He can be concerned about each individual water droplet as He is also concerned about you and how your feelings and everything. So right, He's infinite in His power and His knowledge and in His control of all the little things and bringing everything in to detail, right? So that is the awesomeness of our God. And so we can take great pleasure in watching the rain, right? Because we can see what the Lord is doing with rain. So then we have these two, sublimation and deposition. So what is up with this stuff? Well, so these two are less common on Earth. So they do, because they require kind of extreme temperatures or changing temperatures, shifting quite intensely all of a sudden, or pressures. So we don't see it too often, though. In Canada, we do see sublimation deposition pretty often, or fairly often. Normally in the winter, maybe not once or twice in the winter, so I shouldn't say fairly often. But yeah, when you see water vapor that turns to frost on trees and grass, that is deposition. It's like you can see the word deposit in there. It kind of deposits this water vapor, which is a vapor, hits the cold trees and cold different objects, and it just freezes onto them immediately, going from a gas to a solid, right? And that's pretty incredible. It makes these beautiful scenes. I don't know if you've ever seen this, where everything is just covered in this layer of ice. It's pretty awesome. This again is kind of unique. It doesn't happen very often because normally when there's water vapor in the air, it's hot, it's warm, and then it's not going to freeze on anything. So that's kind of it's sort of a weird temperature that would be creating that, or weird weather at that point. And then another thing that we can see on Earth, but this doesn't happen normally that very naturally, but there's this stuff of dry ice, right? So dry ice is a solid material, and when you put it in room temperature, it goes directly from a solid material to a gas, and this is an example of sublimation. So that is pretty interesting. So tomorrow we will review chemical versus physical change and what happens to matter when we are done using it, which we remember was the recycling stuff. And then we'll start by probably Wednesday. We'll start going ahead and relearning about things. So today I hope you also have a chance to work on that experiment. So your first experiment is with an ice cube and figuring out the weight of the ice cube. So it should be fine on a kitchen scale to figure out the weight there. If you do not have a kitchen scale, this kind of might be a bit more difficult for you, and maybe instead of weight, you can kind of look into doing a bit of an experiment on how ice and water, what is the size of the area that it will take up when it freezes and melts. So you might have to get something thin and something see-through, and then make a little marking on a see-through glass, and put the water in, and then see if that, when you freeze it, does it change. So I hope that you all have a scale. If you don't, just contact me and I can edit the experiment for you. So yeah, just read through this. In the hypothesis section, you have to do first before you start the experiment, and that's because the hypothesis is basically what you think will happen and why. So yeah, just make sure you do that first, because if you've already done the experiment, then you won't really be able to make an honest hypothesis because you'll know what happened. So anyways, thank you very much for watching. Hope you have a good rest of your day. And yeah, I look forward to giving you more videos soon.